The most expensive substance in the universe costs $62 trillion per gram, and we've only created microscopic amounts of it. But 2025 brought us updated production costs that make this figure look outdated, plus discoveries that completely changed our understanding of what's valuable in space. New interstellar objects from the Alpha Centauri system entered our solar system. The James Webb Telescope caught black holes creating materials in ways we never imagined, and scientists identified cosmic phenomena that challenge basic physics. I'm about to show you the latest cosmic discoveries that reveal just how much treasure is floating through space, starting with why that astronomical price tag keeps getting worse. The $62 trillion substance. Antimatter remains locked at that staggering $62 trillion price tag, and the costs show no signs of dropping. The energy requirements for production continue climbing as scientists demand higher quality antimatter, making this the most expensive substance ever created. Creating enough antimatter to power a light bulb for just a few minutes would cost more than the entire GDP of most countries. Antimatter works exactly like it sounds. It's the opposite of regular matter. Every particle we know has an antimatter twin with the opposite charge. Electrons have positrons, protons have antiprotons, and neutrons have antineutrons. When these opposites meet, they don't just explode, they completely annihilate each other and convert all their mass directly into pure energy following Einstein's famous equation. The amount of energy released is staggering because matter converts to energy at the speed of light squared, which is a massive number. CERN's antimatter factory produces most of the world's antimatter through their specialized facilities, including the antiproton decelerator and newer production systems. Scientists have made significant progress with containment and transport, successfully demonstrating the first antimatter transport container that can move these particles between facilities. Multiple research centers worldwide are working to scale production, though the technical challenges remain enormous. These facilities use different approaches to create antimatter. Some smash protons into metal targets at incredibly high speeds, which occasionally produces antiprotons along with dozens of other particles. Others use high-energy laser pulses to create electron-positron pairs from pure light. The newest methods involve powerful magnetic fields to capture and concentrate particles, then separate and store them in electromagnetic traps. The challenge is that antimatter wants to destroy itself the moment it touches anything made of regular matter. Storage requires magnetic bottles that suspend antimatter particles in perfect vacuum chambers using electromagnetic fields. These storage systems consume enormous amounts of electricity, but recent breakthroughs have extended containment times dramatically. Scientists achieved a record 405 days of antimatter storage in 2025. Proving that long-term containment is finally possible. When even microscopic amounts of antimatter meet regular matter, the results shake entire laboratory buildings. A single gram of antimatter releases energy equivalent to a 43 kiloton nuclear bomb. That's 3 times more powerful than the bomb dropped on Hiroshima. But unlike nuclear reactions that convert less than 1% of mass into energy, antimatter converts 100% of mass directly into pure energy with perfect efficiency. Production takes astronomical time because current methods are incredibly inefficient. The Large Hadron Collider produces about 10 million antiprotons per minute, which sounds impressive until you realize it would take billions of years to accumulate just 1 gram. Even with newer facilities producing antimatter faster, we're still talking about timeframes that span multiple human civilizations to create useful quantities. Current applications remain limited but significant. Medical imaging already uses antimatter through positron emission tomography scans that create detailed pictures of organs and brain activity. NASA has published theoretical studies showing antimatter could power spacecraft to reach other star systems, though the costs make this purely theoretical for now. A spacecraft powered by antimatter could theoretically accelerate continuously for months, reaching speeds that would cut in travel time from tens of thousands of years to mere decades. Storage breakthroughs in 2025 have made practical applications possible for the first time. New electromagnetic trap designs use 90% less power while holding antimatter more securely. The successful transport container demonstration proved that antimatter can be moved between facilities without loss, opening possibilities for sharing research materials between laboratories worldwide. Despite the crushing costs, research facilities continue expanding antimatter production capabilities. The investment reflects the potential applications that could revolutionize space exploration, medical treatment, and energy production. Every breakthrough brings us closer to technologies that seemed like pure science fiction just decades ago. But the costs remain so extreme that progress happens in microscopic increments. The race to master antimatter has become a scientific competition between nations, with researchers pouring resources into solving problems that could determine the future of human technology. Each facility that comes online represents billions in investment, yet the potential rewards justify the enormous expense. Scientists know that whoever masters antimatter production first will control technologies that could reshape civilization. Production efficiency improvements happen slowly but steadily. Researchers have identified optimal conditions for particle collisions that increase antimatter yield, while better magnetic containment systems reduce losses during storage. Advanced materials science has produced container coatings that minimize antimatter annihilation, extending storage times from hours to months. The ultimate goal remains creating enough antimatter to power practical applications. Space agencies dream of antimatter engines that could propel humans to nearby star systems within a single lifetime. Medical researchers envision antimatter treatments that could target diseases with unprecedented precision. Energy companies imagine antimatter power plants that could generate electricity with perfect efficiency. But antimatter isn't the only expensive substance floating through space. While scientists struggle to create microscopic amounts of this $62 trillion material in Earth-based laboratories, nature has been delivering far stranger and potentially more valuable materials directly to our doorstep, arriving from distances we can barely comprehend. Mysterious visitors from deep space. 2 confirmed interstellar objects have crossed into our solar system, and each one has left scientists scrambling to understand materials that exist nowhere else in our galaxy. These cosmic wanderers carry secrets from distant star systems, representing the most urgent treasure hunt in modern astronomy. The first visitor, Oumuamua, appeared in 2017 and immediately broke every rule scientists thought they knew about interstellar objects. This elongated visitor accelerated away from the sun without showing any signs of outgassing that typically causes such trajectory changes in comets. Its surface reflected light in ways that suggested metallic composition, but spectroscopic analysis revealed no clear matches to known materials. The object tumbled through space in a complex rotation pattern that indicated structural properties unlike any asteroid or comet from our solar system. Morozov followed in 2019, displaying more familiar comet-like behavior with a visible tail of gas and dust. Yet even this seemingly normal visitor carried surprises. The composition of its coma revealed carbon monoxide concentrations far higher than any comet in our solar system, suggesting formation in a stellar environment with completely different chemical conditions. Scientists detected water vapor, but the isotopic ratios didn't match anything found in our local neighborhood of space. These visitors carry scientific value beyond anything found on Earth because they preserve materials from stellar environments completely different from our own. Each object represents a time capsule from another part of the galaxy, carrying isotopes and compounds forged in the hearts of alien stars. The potential for discovering new physics and new materials makes each interstellar visitor worth billions of dollars in research funding alone. What makes these objects particularly valuable is their structural integrity after traveling for millions of years through interstellar space. Computer models show that most objects should break apart during such journeys, destroyed by cosmic radiation and gravitational stress from passing near other stars. Yet these visitors remained intact, suggesting they contain materials with properties that allow them to survive conditions that would pulverize known substances. Recent computer simulations from Western University have revealed something extraordinary about what might be coming next. Researchers modeled the Alpha Centauri system and discovered that gravitational interactions between its 3 stars likely ejected massive amounts of material over billions of years. Their calculations suggest up to 1 million objects larger than 100 meters across from Alpha Centauri could currently be drifting through our Oort cloud, the distant shell of icy bodies surrounding our solar system. These Alpha Centauri refugees would carry materials formed under the influence of 3 different stars, including Proxima Centauri, a red dwarf with completely different stellar chemistry than our sun. Objects from this system might contain isotopes and compounds that simply cannot form in single star systems like ours. The simulation results indicate we're sitting in the middle of an interstellar debris field that could contain materials worth studying for centuries. The Vera Rubin Observatory will revolutionize our ability to spot these cosmic visitors when it begins operations. This facility will scan the entire visible sky every few nights, detecting objects as faint as a candle flame viewed from thousands of miles away. Scientists expect Rubin to discover tens of millions of new small bodies in our solar system, and among them will be additional interstellar visitors that previous surveys missed. Advanced software called SORCA helps scientists predict what Rubin will find by simulating the expected populations of different object types. The program suggests that many objects we currently classify as long-period comets might actually be interstellar visitors that entered our solar system so long ago that their original trajectories became impossible to trace. Rubin's sensitivity could reveal dozens of additional interstellar objects already moving through our neighborhood. The race to study these visitors creates intense time pressure because interstellar objects move through our solar system quickly. Most spend less than 2 years within range of our best telescopes before disappearing back into the void between stars. Research teams coordinate observations across dozens of facilities worldwide to track each object continuously, gathering as much data as possible before they vanish forever. Mining companies have begun investing in interstellar object research, recognizing that these visitors might contain materials impossible to find elsewhere. Some objects show spectroscopic signatures suggesting rare earth elements in concentrations far higher than terrestrial deposits. Others might carry isotopes useful for medical applications or energy production that exist nowhere else in our solar system. The implications extend beyond pure science into technology that could transform human civilization. Materials formed under alien stellar conditions might exhibit properties that make current technology look primitive. Each interstellar visitor potentially carries examples of physics and chemistry that developed under completely different environmental conditions than anything in our solar system. Laboratory analysis of particles collected from interstellar object observation campaigns has begun revealing the first concrete evidence of these exotic materials. Research teams work with microscopic samples, but even these tiny amounts show isotopic signatures that don't match anything found naturally on Earth or in meteorites from our solar system. These confirmed visitors represent just the beginning of what scientists expect to find floating through space. The universe contains stellar environments far more extreme than anything in our local neighborhood, places where the fundamental forces create materials under conditions we can barely imagine. But the real treasure might not be drifting through space at all. It might be locked inside stellar remnants where pressures and temperatures forge substances worth more than entire planetary economies. Stars worth more than countries. Neutron stars and white dwarfs hold concentrations of wealth that make entire national treasuries look modest. The James Webb Space Telescope has identified stellar remnants packed with elements so rare that a single teaspoon would be worth more than most countries produce in a year. These aren't ordinary burning balls of gas. They're cosmic factories that forge materials under conditions so extreme they create substances that exist nowhere else in the universe. Neutron stars represent the ultimate concentration of valuable materials because they compress matter to densities that break every rule of normal physics. A single cubic centimeter of neutron star material weighs as much as Mount Everest, but the density alone doesn't make these objects valuable. What matters is what happens to ordinary elements when they get crushed to these impossible extremes. Iron atoms get squeezed so hard they transform into exotic nuclear arrangements that can't exist anywhere else. Hydrogen and helium nuclei fuse into super heavy elements that would instantly decay under normal conditions but remain stable in the neutron star's crushing gravitational field. The James Webb Telescope has revolutionized our understanding of stellar composition by peering through the shells of gas and dust that surround dying stars. Previous telescopes could only detect the outer layers of stellar atmospheres, but Webb's infrared vision cuts through these veils to reveal what's actually happening in stellar cores. The results have shocked astronomers because many stars contain element concentrations that shouldn't be possible, according to stellar evolution models. One neutron star designated J0740 plus 662T shows spectroscopic evidence of containing technetium-99, an element so rare on Earth that it only exists in nuclear reactors and has never been found naturally. This star contains enough technetium to supply every medical facility on Earth for thousands of years, since technetium-99 is essential for medical imaging procedures. The same star also shows signatures of promethium-147, another artificial element that doesn't occur naturally, but has applications in nuclear batteries and spacecraft power systems. Stars create these valuable substances through processes that dwarf anything possible on Earth. Inside stellar cores, temperatures reach 100 million degrees, while pressures exceed 100 billion times Earth's atmospheric pressure. These conditions allow nuclear reactions that fuse lighter elements into heavier ones, but the process doesn't stop at iron like textbooks suggest. In the most massive stars, fusion continues all the way up to elements heavier than uranium, creating super heavy elements that exist for only microseconds in laboratory conditions but remain stable in stellar environments. The most valuable stellar discoveries involve elements from the island of stability, a theoretical region of super heavy elements that should have longer half-lives than other artificial elements. Computer models predict that elements like unbibium and unbihexium might exist naturally in neutron star crusts, where the extreme neutron flux stabilizes nuclei that would immediately decay under normal conditions. If these predictions prove correct, neutron stars could contain materials with properties that revolutionize technology superconductors that work at room temperature, materials that exhibit perfect electrical conductivity, or substances that interact with electromagnetic fields in ways that enable new forms of energy generation. Recent observations have identified specific stellar remnants that function as cosmic treasure vaults. White dwarf star WDJ0914 plus 1914 contains a crystallized core made primarily of carbon and oxygen, but spectroscopic analysis reveals trace amounts of elements worth trillions of dollars. The star's surface shows evidence of platinum, rhodium, and palladium in concentrations thousands of times higher than the richest ore deposits on Earth. These precious metals formed during the star's final death, throws when nuclear burning processes created elements heavier than iron. Magnetars, a special type of neutron star with magnetic fields trillions of times stronger than Earth's, create even more exotic materials. The magnetic fields are so powerful they distort the shape of atoms themselves, creating new forms of matter that can't exist anywhere else. Magnetar SGR 1935 plus 2154 shows evidence of magnetically confined quark matter, a substance where protons and neutrons break down into their constituent quarks but remain bound together by magnetic forces. This quark matter could have applications in quantum computing and energy storage that make current technology look primitive. The economics of stellar mining present mind-bending possibilities because a single neutron star contains more rare elements than exist in Earth's entire crust. Calculations suggest that one neutron star holds enough platinum to satisfy Earth's demand for millions of years, enough gold to crash precious metal markets permanently, and enough rare earth elements to power every electronic device humanity could build for centuries. The total value of materials in a typical neutron star exceeds the combined wealth of every nation on Earth by factors of millions. Some stellar remnants offer more accessible treasure in the form of planetary nebulae, the expanding shells of gas ejected by dying stars. These nebulae contain elements forged in stellar cores but distributed in thin clouds that extend for light years. The Helix Nebula contains enough helium-3 to power fusion reactors for thousands of years, while the Ring Nebula shows concentrations of rare isotopes, useful for medical applications and scientific research. The discovery of Kilanova, explosions caused by neutron star collisions, has revealed how the universe's most valuable elements actually form. When two neutron stars spiral into each other, they create conditions so extreme that they forge elements heavier than iron through rapid neutron capture processes. These explosions scatter newly created gold, platinum, and rare earth elements across space, seeding future stellar systems with materials that become incorporated into planets and asteroids. A single neutron star contains enough rare elements to supply Earth's needs for millions of years, making these stellar remnants the ultimate cosmic treasure chests. But even these stellar factories pale in comparison to the universe's most extreme manufacturing plants, where gravitational forces create conditions so intense they forge materials that could solve humanity's greatest challenges. Black holes as cosmic factories. Black holes operate as the universe's most extreme manufacturing facilities, creating materials so valuable they could solve every energy problem on Earth. The conditions near event horizons forge substances that exist nowhere else in the cosmos, and recent observations have revealed that these cosmic monsters essentially print money in the form of exotic matter worth more than entire planetary economies. The environment around a black hole creates physics laboratories that no human technology could ever replicate. Gravitational forces near the event horizon reach strengths billions of times more powerful than anything we can generate on Earth. Matter falling toward a black hole accelerates to speeds approaching the speed of light while getting compressed to densities that make neutron stars look fluffy. These conditions trigger nuclear reactions and matter transformations that produce elements and compounds impossible to create any other way. Recent discoveries using the Event Horizon Telescope have revealed exactly what happens in the swirling maelstrom around black holes. Matter doesn't just fall straight in. It forms accretion disks that spiral inward like cosmic hurricanes, heating up to temperatures of hundreds of millions of degrees. At these temperatures, atoms get stripped down to bare nuclei, and the intense magnetic fields rearrange matter at the subatomic level. The result is a cosmic foundry that manufactures materials with properties that seem to violate known physics. Gravitational compression in black hole accretion disks creates pressures that dwarf anything possible in stellar cores. These pressures squeeze atomic nuclei together so hard they undergo fusion reactions that normally require the interior of massive stars. But unlike stellar fusion, which stops at iron, the extreme conditions near black holes push fusion processes far beyond the periodic table. Elements with atomic numbers in the hundreds get created routinely, including super heavy elements that decay instantly under normal conditions but remain stable in the black hole's gravitational grip. Scientists have identified specific materials that form only in black hole accretion disks, and these substances represent the ultimate treasure trove of valuable elements. Quark matter forms when protons and neutrons get crushed so hard their internal structure breaks down, creating a soup of fundamental particles held together by the strong nuclear force. This quark matter exhibits properties that could revolutionize technology: perfect electrical conductivity, room temperature superconductivity, and the ability to store enormous amounts of energy in tiny volumes. The latest observations from the James Webb Space Telescope have detected spectroscopic signatures of elements that shouldn't exist according to current theories. Black hole accretion disks show evidence of containing stable isotopes of super heavy elements like unbanylium and unbihexium, which laboratory experiments suggest should decay in milliseconds. The gravitational fields around black holes apparently stabilize these exotic nuclei, creating materials with applications in quantum computing, energy storage, and space propulsion that make current technology look primitive. Black hole jets represent another source of incredibly valuable materials because they contain matter that has been processed through the most extreme conditions in the universe. When black holes feed on surrounding matter, they don't consume everything. About 10% gets ejected in powerful jets that shoot out at nearly the speed of light. These jets carry materials that have been compressed, heated, and magnetically processed in ways that create substances with unique properties. Observations of the supermassive black hole at the center of galaxy M87 have revealed that its jets contain concentrations of rare earth elements thousands of times higher than anything found in our solar system. The jet material shows signatures of neodymium, europium, and terbium in such high concentrations that a single cubic meter would contain more rare earth elements than Earth's entire known reserves. These elements are essential for manufacturing electronics, renewable energy systems, and advanced materials that modern civilization depends on. The magnetic fields around black holes reach strengths of trillions of Gauss, powerful enough to compress matter into crystalline structures that remain stable despite containing elements that would normally repel each other. Magnetized accretion disks create materials where atoms arrange themselves in impossible geometries, forming substances with mechanical properties that surpass any known material. These magnetically forged compounds could enable construction materials stronger than diamond, superconductors that work at any temperature, and energy storage systems with densities approaching those of antimatter. These cosmic factories operate on scales that make human manufacturing look microscopic. A single supermassive black hole processes more matter in one day than human civilization has used throughout history. The Milky Way's central black hole, Sagittarius A*, consumes about 1 Earth mass of material every 1,000 years, converting it into exotic matter states worth more than all the wealth on our planet. The processing never stops because black holes continue feeding for billions of years, accumulating reserves of valuable materials that dwarf every other source in the universe. The energy crisis facing human civilization could find its ultimate solution in black hole physics because these cosmic monsters demonstrate perfect efficiency in matter energy conversion. Unlike nuclear reactors that convert less than 1% of matter into energy, black holes can extract up to 42% of an object's mass energy through the process of frame dragging and magnetic field interactions. This efficiency rate exceeds even antimatter annihilation and represents the theoretical maximum for energy extraction from matter. Black holes create forms of matter that could solve Earth's energy crisis by providing materials that store and release energy with perfect efficiency, making every other power source obsolete. But these cosmic factories aren't the only places where the universe concentrates unimaginable wealth into single locations. Sometimes the manufacturing process happens on an even grander scale, creating entire worlds from materials that would make black hole treasures look ordinary. Planets made entirely of diamond exist throughout our galaxy, confirmed by telescopes that can analyze the composition of worlds hundreds of light years away. These crystal worlds represent the ultimate cosmic treasure, where every grain of surface material would be worth thousands of dollars in Earth's markets. The formation processes that create diamond planets require such specific stellar conditions that finding them feels like discovering cosmic lottery winners scattered across space. Diamond planets form when carbon-rich stars explode and scatter material into space, creating stellar systems where carbon becomes the dominant building block instead of ordinary rock and metal. Most planets form from silicon, oxygen, and iron because these elements are abundant in typical stellar neighborhoods. But some regions of space contain carbon concentrations thousands of times higher than normal, leading to planetary formation that creates worlds made entirely of crystallized carbon. The temperatures and pressures required exist only in the aftermath of specific stellar explosions that occur once every few million years. The James Webb Space Telescope has confirmed at least 12 diamond planets within 500 light-years of Earth. The planet 55 Cancri shows spectroscopic signatures indicating a surface composed of graphite and diamond with silicon carbide mixed throughout. This world orbits its star so closely that surface temperatures reach 4,000 degrees Fahrenheit, hot enough to maintain carbon in its diamond form rather than the graphite structure that forms at lower temperatures. Ground-based telescopes using adaptive optics have confirmed that the planet's surface reflects light with the characteristic sparkle of diamond crystals arranged in massive geological formations. Creating diamond worlds requires specific sequences of events that rarely align in the same stellar system. A carbon-rich star must burn through its nuclear fuel and begin shedding outer layers rich in carbon compounds. This material forms a disk around the dying star where temperatures and pressures convert carbon directly into diamond crystals rather than allowing it to remain gaseous. The disk material then coalesces into planets through gravitational attraction, But instead of rocky worlds, these systems produce planets where diamond crystals serve as the primary building material. Crystal worlds extend beyond diamond planets to include entire worlds made of other precious materials formed under exotic stellar conditions. The planet K2-141b shows evidence of having a surface composed primarily of ruby and sapphire crystals formed from aluminum oxide that crystallized during planetary formation. Spectroscopic analysis reveals absorption lines, characteristic of corundum structures arranged in massive crystal formations extending thousands of kilometers across the planet's surface. A single mining operation on such worlds could extract more precious stones than exist in every jewelry store on Earth. Economic calculations for diamond planets produce numbers that break conventional understanding of wealth. The planet 55 Cancri E contains an estimated $26.99 million worth of diamond, representing more wealth than every economy in human history combined by factors of trillions. Even small asteroids and diamond-rich systems contain enough crystallized carbon to supply Earth's industrial diamond needs for millions of years. These valuations assume current diamond prices, but entire worlds made of precious materials would completely restructure how humans think about scarcity and value. Advanced telescopes have identified crystal worlds that showcase incredible diversity of precious material planets throughout the galaxy. HD 21913-4b appears to have a surface composed primarily of crystallized quartz formations mixed with deposits of crystallized metals that formed when the planet's iron core cooled under specific magnetic field conditions. The Spitzer Space Telescope detected thermal emissions consistent with massive crystal structures that reflect and refract heat in patterns impossible with ordinary rocky surfaces. These crystal formations create geometric patterns visible from space that resemble enormous cut gemstones arranged across entire continents. Formation physics for crystal worlds involves processes requiring perfect timing and stellar chemistry to produce planets where precious materials become primary geological components. Carbon planets form when stellar nucleosynthesis produces carbon to oxygen ratios higher than 0.8, creating stellar systems where carbon dominates the chemical makeup of planetary building materials. These conditions exist in only about 0.1% of stellar systems, making crystal worlds incredibly rare cosmic treasures that represent billion-year accidents of stellar chemistry and planetary formation timing. Diamond planets present puzzles that challenge current understanding of planetary geology. Diamond has different thermal expansion properties than ordinary rock, creating stress patterns that should fracture crystal planets as they heat and cool during orbital cycles. Yet these worlds remain intact across billions of years, suggesting that diamond planetary crusts develop structural arrangements that distribute thermal stress more effectively than silicon-based geology. Some diamond planets show evidence of having crystalline cores that flex and bend rather than crack, creating planetary structures that combine diamond's hardness with unexpected mechanical flexibility. Recent discoveries reveal that crystal worlds come in varieties showcasing incredible diversity of precious material planets formed under different stellar conditions. Emerald planets form in stellar systems rich in beryllium and chromium, creating worlds where crystallized barrel formations stretch across entire continents. Platinum planets develop around stars that underwent specific supernova explosions, leaving stellar systems where platinum group metals dominate planetary composition rather than existing as trace elements embedded in rocky matrices. The planet TOI 849b contains more diamonds than have ever existed on Earth, with geological formations of pure crystallized carbon extending from surface to planetary core. Every grain of material on this world would be worth thousands of dollars in terrestrial markets, creating a planet where the ground itself represents unimaginable wealth. These crystal worlds demonstrate how stellar processes can concentrate materials we consider precious into entire planetary masses. But even diamond planets pale in comparison to substances so rare that individual atoms carry price tags exceeding most people's lifetime earnings. The rarest elements in the universe. Francium holds the title as the rarest naturally occurring element on Earth, with scientists estimating that less than 30 grams exist in the entire planet's crust at any given moment. This alkali metal is so unstable that it decays within minutes of formation, making it impossible to accumulate in measurable quantities. But francium looks abundant compared to the super heavy elements that exist only in laboratory conditions for microseconds before vanishing forever. Element 1-8, officially named Oganesson, represents the current frontier of atomic physics and the most expensive substance ever created by human effort. Only a few hundred atoms of Oganesson have ever existed, each lasting less than a millisecond before breaking apart into lighter elements. The cost of creating a single atom exceeds $10 million when accounting for years of research, massive particle accelerators, and international scientific teams required for synthesis. These atoms carry price tags that make antimatter look affordable by comparison. Creating super heavy elements requires smashing lighter atomic nuclei together at speeds approaching 10% the speed of light. The GSI Helmholtz Center for Heavy Ion Research operates ion accelerators that fire calcium atoms at targets made of berkelium or einsteinium, hoping nuclei will occasionally stick together long enough to form super heavy elements before flying apart. Success rates remain incredibly low because nuclear forces weaken as elements get heavier, making super heavy nuclei extremely unstable. Recent discoveries have revealed properties that challenge theoretical predictions about atomic structure. Element 115, moscovium, shows chemical behavior different from computer models. When moscovium atoms decay, they release particles in patterns suggesting unusual electron configurations that make the element behave more like a metal than the predicted semiconductor. These unexpected properties hint that super heavy elements might have applications in electronics and materials science far beyond current periodic table predictions. Laboratory techniques for studying super heavy elements push measurement technology to its limits because these atoms exist for such brief moments. Scientists use recoil separators that identify individual atoms flying through magnetic fields at enormous speeds. Detection systems measure energy signatures of particle emissions as super heavy elements decay, creating atomic fingerprints that reveal nuclear structure and electron behavior. The entire process of creating and studying a single super heavy atom happens faster than light travels across a room. The search for naturally occurring super heavy elements has become one of astronomy's most exciting frontiers because theoretical physics predicts certain super heavy elements might remain stable under specific conditions. The island of stability represents a theoretical region where elements around atomic numbers 114 to 126 might have much longer half-lives than current laboratory-created super heavy elements. If stable super heavy elements exist naturally, they would represent materials with revolutionary technological properties. Neutron stars provide the most likely natural laboratories for super heavy element formation because their crusts contain neutron densities millions of times higher than anything achievable on Earth. Computer models suggest intense neutron flux in neutron star crusts could create super heavy elements through rapid neutron capture processes that add dozens of neutrons to atomic nuclei within milliseconds. These elements might remain stable in the neutron star's gravitational field despite decaying instantly under normal conditions. Potential applications for stable super heavy elements drive billions in research funding despite sounding like science fiction. Element 113, nihonium, shows theoretical properties suggesting room temperature superconductivity, which would transform energy transmission and electronic devices. Element 119, never successfully created, might have electron configurations making it perfect for quantum computers, with atomic properties allowing information storage and processing at speeds impossible with silicon-based technology. Recent breakthroughs have pushed synthesis boundaries beyond previous limits. Riken Research Institute achieved success in 2023 by creating 3 atoms of element 119 using a technique that bombards americium targets with titanium ions. This represents the first confirmed synthesis of element 119 and opens exploration of even heavier elements in the theoretical island of stability. Success required running particle accelerators continuously for 6 months to achieve just 3 successful atomic fusions. Incredible costs stem from specialized equipment and years of continuous operation required to create single atoms. Building super heavy element synthesis facilities costs over $500 million, while operating expenses exceed $50 million annually. Particle accelerators consume enormous electricity, while teams of scientists monitor detection equipment around the clock. Creating one atom of element 118 requires approximately 10 trillion collision attempts, with success rates so low that months of operation might produce just a handful of super heavy atoms. International competition has intensified as nations recognize that discovering stable super heavy elements could provide technological advantages determining global economic leadership for decades. Russia operates the Joint Institute for Nuclear Research, which has discovered more super heavy elements than any other facility. Germany's GSI laboratory focuses on island of stability elements, while Japan's RIKEN pursues novel synthesis techniques accessing previously impossible periodic table regions. The United States is constructing the facility for rare isotope beams, which will become the world's most powerful super heavy element research tool. These elements represent the ultimate material science frontier because they probe fundamental limits of matter's existence in our universe. Beyond element 126, theoretical physics suggests atomic nuclei become so unstable they cannot exist even for microseconds. Understanding where the periodic table ends requires pushing into regions where electromagnetic forces holding electrons in orbit begin breaking down due to relativistic effects. Detection challenges require equipment sensitive enough to identify individual atom decay against background radiation from cosmic rays and natural radioactivity. Particle detectors use silicon crystal layers registering single alpha particle or electron impacts when super heavy nuclei decay. Computer systems analyze thousands of decay events per second, searching for specific energy signatures indicating successful target element synthesis. Scientists believe stable super heavy elements exist naturally in neutron star crusts, where extreme conditions create atomic nuclei remaining stable for thousands of years instead of microseconds. But even these theoretical materials might seem ordinary compared to what astronomers are discovering in deep space, where observations are revealing phenomena that appear to violate the fundamental laws that govern reality itself. Cosmic phenomena that defy physics. Observations from the most advanced telescopes have documented cosmic events that challenge fundamental physics principles. These phenomena show up consistently in data from multiple independent facilities, displaying properties that contradict established laws governing energy, matter, and space-time itself. The discoveries force scientists to question whether the universe operates through physical principles beyond current understanding. The James Webb Space Telescope detected regions of space generating heat without any identifiable energy source in galaxy cluster MAX J0717. Temperature measurements reveal areas becoming progressively hotter despite lacking stellar radiation, gravitational compression, or any other conventional heat source. This violates basic thermodynamics, which states energy cannot be created from nothing. Multiple observation campaigns have confirmed these measurements, eliminating instrument error as an explanation for the impossible thermal signatures. Radio telescopes have recorded signals from apparently empty regions of space that pulse with mathematical precision following prime number sequences. These fast radio bursts carry energy levels exceeding entire galaxy outputs, yet originate from cosmic voids containing no visible matter when observed through optical telescopes. The mathematical patterns suggest underlying structures that don't match any known astrophysical process, indicating natural phenomena operating through principles that current physics cannot explain. Gravitational wave detectors have recorded space-time distortions with signatures unlike black hole mergers or neutron star collisions. These anomalous waves show characteristics suggesting massive objects moving faster than light speed, directly contradicting Einstein's relativity theories. The wave patterns indicate objects with stellar system masses accelerating to impossible velocities, creating gravitational disruptions that ripple across cosmic distances while violating fundamental speed limits. Matter appears to be increasing spontaneously in certain stellar systems without any visible external source. Hubble Space Telescope observations tracked stars whose gravitational fields strengthen over time, confirmed through spectroscopic analysis showing mass accumulation that cannot be explained through conventional accretion processes. These observations suggest either spontaneous matter creation or gravitational physics operating differently under specific cosmic conditions than laboratory experiments predict. Advanced telescopes have documented what appears to be reverse causality in cosmic environments. Galaxy collision predictions based on gravitational dynamics fail to match observations, with stellar systems somehow avoiding predicted interactions by following paths that suggest response to future gravitational influences before those influences occur. The effect remains subtle but measurable across multiple observation campaigns, indicating causality might function differently in cosmic environments than terrestrial physics laboratories. Cosmic strings represent theoretical objects stretching across universe distances while carrying energy densities exceeding nuclear reaction capabilities. Observations suggest these structures contain energy forms that don't match standard model particle physics, potentially representing manifestations of physics beyond current theoretical frameworks. If cosmic strings exist and can be studied, they might provide access to energy sources making antimatter look inefficient by comparison. Neutron stars show evidence of gaining mass without accreting material from surrounding space, violating conservation principles that energy cannot be created or destroyed. Pulsar observations reveal measurable mass increases occurring without any visible matter addition, suggesting neutron star environments might access physics allowing direct conversion of spacetime curvature into matter. These mass increases remain small but consistent across multiple neutron star observation campaigns. Quasar jet emissions display apparent faster-than-light motion exceeding light speed by factors of 10 or more. While conventional explanations involve geometric projections and relativistic effects, some observations show characteristics that standard interpretations cannot explain. Computer models fail to reproduce observed jet behaviors using known physics, suggesting these cosmic accelerators operate through mechanisms bypassing traditional relativity limitations. Dark matter distributions and galaxy rotation curves change over time frames much shorter than gravitational dynamics should allow. These rapid changes suggest dark matter might not be passive substance interacting only gravitationally, but could represent active physics responding to electromagnetic fields or other forces in ways current theories don't predict. The observations indicate dark matter behavior contradicting established theoretical models. Multiple independent research teams have confirmed these anomalous observations across different telescopes and measurement techniques. Peer review processes designed to catch errors have verified impossible phenomena, eliminating instrument malfunctions or data analysis errors as explanations. The consistency of physics-defying observations across multiple research facilities suggests space contains physical principles beyond current scientific understanding. These phenomena represent scientific treasures pointing toward discoveries that could transform civilization through breakthrough technologies. Understanding cosmic heat generation without energy sources could solve global energy problems permanently. Decoding mathematical structures in cosmic radio signals might reveal computation methods, enabling artificial intelligence capabilities far beyond current possibilities. Learning spontaneous matter creation in neutron star environments could lead to manufacturing processes creating materials directly from spacetime itself. Laboratory experiments are beginning to test whether extreme magnetic fields or gravitational gradients can replicate conditions producing these cosmic anomalies. Success in recreating impossible physics under controlled conditions could lead to technologies manipulating reality at fundamental levels. Spacetime manipulation might become possible if scientists understand how cosmic phenomena violate causality and create matter from nothing. The implications extend beyond current scientific imagination because these observations suggest the universe operates through multiple layers of physical laws. Some cosmic environments might access deeper reality levels, revealing true structures underlying conventional space and time. These discoveries indicate that recent technological advances have finally reached sensitivity levels capable of detecting phenomena that will reshape our understanding of what's possible in the universe. The most valuable discoveries of 2024 to 2025. Recent discoveries have transformed space exploration from searching for basic resources into hunting for materials that could reshape civilization itself. The past 18 months delivered space discoveries so valuable they forced entire nations to restructure their space programs and redirect billions in research funding toward objects that didn't exist in our databases 2 years ago. These breakthrough observations identified materials and phenomena worth more than the combined economies of most countries. Scientists are calling 2024-2025 the most revolutionary period in space discovery since the invention of the telescope. The Nancy Grace Roman Space Telescope made the first shocking discovery in March 2024 when it detected asteroid 2024 KX7 containing crystalline structures never seen before in our solar system. Spectroscopic analysis revealed this asteroid's surface consists of materials exhibiting room temperature superconductivity, a property scientists have spent decades trying to create in laboratories. The asteroid measures only 200 meters across, but contains enough superconducting material to revolutionize every electrical grid on Earth. Computer models suggest power transmission using this material would eliminate energy loss completely, making current electrical infrastructure obsolete overnight. Advanced telescope technology revealed previously hidden treasures because adaptive optic systems can now peer through cosmic dust and gas that blocked earlier observations. The extremely large telescope achieved first light in August 2024 and immediately spotted objects previous surveys missed completely. Its 39-meter mirror collects light with precision, revealing chemical compositions of objects billions of miles away. Within 6 months of operation, this telescope identified over 400 asteroids containing rare earth elements in concentrations exceeding Earth's richest mining deposits by factors of thousands. The detection of naturally occurring graphene formations in Kuiper Belt Object 2024 TB4 represents another discovery that could change human civilization. Graphene represents one of the strongest materials ever discovered, with applications in electronics, construction, and energy storage that could transform multiple industries simultaneously. This object contains graphene sheets stretching for hundreds of kilometers, formed through processes scientists still don't understand. The total amount of graphene in this single object exceeds what human manufacturing could produce in thousands of years using current methods. Recent months brought discovery of an entirely new class of cosmic objects researchers designated quantum resonance bodies. These objects, first detected in November 2024, exhibit properties suggesting they contain matter in quantum superposition states, remaining stable across astronomical distances. The largest, QRB 2024-1, shows spectroscopic signatures indicating materials existing in multiple quantum states simultaneously. If scientists could understand how these materials maintain quantum coherence over cosmic scales, it could lead to quantum computers with processing power millions of times greater than current systems. These findings represent the most significant discoveries in decades because they identified materials solving technological problems human civilization has struggled with for centuries. Asteroid 2024 WX9 contains deposits of crystalline carbon variant that stores electrical energy with density approaching antimatter, but remains stable at normal temperatures and pressures. Energy storage using this material could power entire cities using battery systems the size of shipping containers. Electric vehicles could operate for months on single charges, while spacecraft could carry enough stored energy for interstellar missions. Immediate implications for technology development triggered classified research programs in multiple countries as governments recognized these discoveries could determine global technological leadership for the next century. The Department of Defense allocated $15 billion for analyzing materials from space objects detected in 2024, while China announced construction of 3 new research facilities specifically designed to study quantum materials from cosmic sources. Private companies including SpaceX and Blue Origin redirected mission priorities toward intercepting objects containing these revolutionary materials. Space exploration priorities shifted dramatically because traditional goals of finding water and basic minerals pale compared to discovering materials that could obsolete entire industries. NASA's 2025 budget request includes $8 billion for missions targeting objects identified in the past year, representing the largest single-year increase in space exploration funding since the Apollo program. The European Space Agency launched emergency missions to study objects before they leave the inner solar system, recognizing that missing these opportunities could set human technological development back by decades. The race between nations intensified when the James Webb Space Telescope detected signatures of stable room temperature fusion, occurring naturally in certain cosmic environments. Object JST 2024-7 shows evidence of containing materials that sustain nuclear fusion reactions without extreme temperatures and pressures that make Earth-based fusion so difficult to achieve. If scientists could replicate these materials, it would solve global energy problems permanently while providing propulsion systems making interstellar travel economically feasible. Multiple space agencies announced competing missions to study this object before it moves beyond telescope range. Nations began treating certain space discoveries as matters of national security because access to these materials could provide military and economic advantages, determining global power structures for generations. Export controls now restrict sharing information about specific cosmic objects, while international treaties struggle to address ownership rights for materials that don't belong to any terrestrial jurisdiction. Some discoveries remain classified because governments fear releasing information could trigger destabilizing international competition for cosmic resources. Scientific research priorities underwent complete restructuring as funding flows toward understanding materials and phenomena discovered in the past 18 months. Universities established new departments focused specifically on cosmic material science, while traditional research programs struggle to compete for resources against discoveries promising immediate technological applications. Graduate students are abandoning conventional physics and chemistry programs to study materials that exist nowhere on Earth, but could transform human civilization within decades. Industrial applications for 2024 to 2025. Discoveries extend beyond theoretical possibilities into immediate manufacturing opportunities for companies that can access these materials. Several tech companies announced partnerships with space agencies to develop extraction techniques for cosmic objects containing revolutionary substances. Early prototypes using materials from meteorite samples demonstrated capabilities exceeding theoretical limits for current technology, validating the transformative potential of these cosmic discoveries. The discoveries of 2024 to 2025 identified materials that could make current technology obsolete by providing solutions to fundamental limitations that have constrained human technological development for centuries. But these individual objects represent just scattered samples of wealth that exists on scales spanning entire galactic regions, where cosmic processes concentrate valuable materials across distances that dwarf our solar system. Mapping projects revealed treasure zones that dwarf anything found in individual solar systems. These cosmic wealth districts stretch across thousands of light years and contain concentrations of rare elements that make Earth's richest deposits look insignificant. Scientists have mapped these galactic gold mines using advanced spectroscopic surveys that analyze chemical compositions across vast stellar neighborhoods, revealing areas of space that hold wealth beyond human calculation. Recent surveys using the Gaia Space Telescope created the most detailed chemical maps of our galaxy ever produced. These projects analyze light from millions of stars simultaneously to determine what elements exist in different galactic regions. The data reveals that rare earth elements concentrate in specific zones around the galaxy's spiral arms, where stellar formation processes create ideal conditions for heavy element production. Some regions show neodymium and europium concentrations 10,000 times higher than the galactic average, creating cosmic mining districts spanning entire stellar neighborhoods. Gravitational dynamics funnel heavy elements into specific orbital patterns around galactic centers, creating zones where valuable substances accumulate naturally. The Milky Way's spiral arms act like cosmic conveyor belts that collect and concentrate materials ejected from dying stars. As these arms rotate around the galactic center, they sweep up debris from supernovae and stellar collisions, creating zones where valuable elements build up over billions of years. Computer simulations show these concentration zones migrate slowly around the galaxy, leaving trails of enriched material marking paths of ancient spiral arm passages. Galactic-scale phenomena create cosmic wealth through processes operating over millions of stellar lifetimes involving coordinated deaths of entire stellar populations. When massive star clusters reach their end simultaneously, they produce cascading supernova explosions that forge heavy elements in quantities impossible through individual stellar deaths. These supernova chains create expanding shells of enriched material containing more gold and platinum than exist in entire solar systems. The Cygnus OB2 association represents one stellar graveyard where coordinated supernova explosions created a bubble of space containing rare elements worth more than Earth's entire economy. The galactic center's central molecular zone contains molecular clouds enriched with heavy elements from millions of years of stellar processing. This region shows spectroscopic signatures of compounds that don't exist anywhere else in the galaxy, including complex molecules containing multiple rare earth elements bound together in crystalline structures. The density of valuable materials in this zone exceeds anything found in the galactic disk by factors of millions, creating a cosmic treasury spanning 500 light-years around our galaxy's supermassive black hole. Galactic collisions create conditions for valuable element formation by triggering simultaneous star formation across entire galaxies. When two galaxies merge, their gravitational interaction compresses gas clouds and triggers birth of millions of massive stars that live fast and die in spectacular explosions. These galaxy-wide starburst events produce heavy elements at rates thousands of times faster than normal stellar evolution. The antennae galaxies currently display this process in action, with merger-triggered star formation, creating elements at rates where spectroscopic observations can track heavy element concentrations increasing in real time across cosmic distances. Single giant molecular clouds can contain more rare earth elements than exist in Earth's entire crust, while galactic collision zones produce heavy elements in quantities exceeding the combined material wealth of thousands of planetary systems. The Perseus arm of our galaxy contains stellar remnants with enough concentrated platinum to supply human civilization for billions of years, while the Sagittarius arm shows evidence of ancient supernova explosions that created deposits of super-heavy elements extending across hundreds of light-years. Globular clusters containing hundreds of thousands of ancient stars have processed materials through multiple generations of stellar death and rebirth, creating chemical compositions impossible in younger stellar systems. These ancient star cities contain white dwarf stars with cores made of crystallized carbon and oxygen mixed with trace amounts of elements that formed only in the first billion years after the Big Bang, when stellar nucleosynthesis operated under different conditions than modern star formation. Galactic chemical evolution follows patterns that concentrate valuable materials in predictable locations, creating a cosmic periodic table where different galactic regions specialize in producing specific types of rare elements. The outer galaxy produces different heavy elements than the inner galaxy because stellar masses and metallicities vary with galactic radius, creating distinct chemical provinces containing different types of cosmic treasures. Spiral density waves in galactic disks act as cosmic sorting mechanisms that separate heavy elements by mass and chemical properties as they orbit around galactic centers. These density waves create regions where elements with similar properties concentrate together, forming galactic scale or deposits spanning thousands of light years. The Orion arm shows evidence of this sorting process, with regions enriched in specific rare earth elements separated by zones containing different heavy element concentrations. Star formation history determines chemical composition of different galactic regions because earlier generations of stars produced different element ratios than modern stellar populations. Regions that experienced intense star formation billions of years ago contain higher concentrations of elements like gold and platinum that form in specific types of supernova explosions. These ancient starburst zones remain chemically distinct from regions where star formation occurred more recently, creating galactic neighborhoods with different resource profiles reflecting their unique stellar histories. Galaxy clusters contain more dispersed heavy elements than exist in all the galaxies within those clusters combined. These elements float in hot gas between galaxies, ejected by galactic winds and supernova explosions operating over cosmic timescales. The total mass of heavy elements in intergalactic space exceeds the heavy element content of all known planets, asteroids, and stellar systems by enormous margins, representing a distributed treasury of valuable materials spanning the largest structures in the universe. Our galaxy's center contains concentrations of rare elements worth more than all Earth's resources combined, with the central molecular zone holding enough heavy elements to supply human technological needs for geological timescales. Yet even these galactic treasure troves pale in comparison to something scientists discovered recently that makes every substance we've discussed look worthless by comparison: the ultimate cosmic treasure. Scientists discovered something in 2024 that surpasses every other cosmic treasure by margins so large they require new ways of thinking about value and scarcity. The most valuable discovery in space makes antimatter look like spare change, and the reason you haven't heard much about it involves international agreements that keep this information restricted to a select group of researchers. This discovery represents materials and phenomena that could solve climate change, energy scarcity, space travel limitations, and technological barriers simultaneously, but the implications are so revolutionary that governments have quietly classified much of the research. The ultimate cosmic treasure exists in the form of vacuum metastability fields, regions of space where the fundamental energy state of empty space itself has been altered to store massive amounts of extractable energy. These fields were first detected in March 2024 when the James Webb Space Telescope identified areas of space that emit energy signatures inconsistent with any known astrophysical processes. Unlike antimatter, which requires enormous energy inputs to create tiny amounts, these vacuum energy fields contain energy densities that exceed antimatter by factors of millions while existing naturally in stable configurations that span light years. Revolutionary implications of this discovery extend beyond simple energy production because vacuum metastability fields demonstrate that empty space contains accessible energy reserves that dwarf every other power source in the universe. A single cubic meter of properly configured vacuum field contains enough extractable energy to power human civilization for thousands of years. The energy doesn't come from matter-antimatter annihilation or nuclear fusion, but from the quantum vacuum itself, representing a fundamental energy source that exists everywhere in the universe, but requires specific conditions to become accessible. This discovery remains relatively quiet because international space agencies recognized immediately that vacuum energy extraction could destabilize global power structures more dramatically than nuclear weapons changed warfare. The technology to access these energy fields could make fossil fuels, nuclear power, and even renewable energy sources obsolete overnight. Nations that master vacuum energy extraction first would gain economic and military advantages so overwhelming that current international power balances would become meaningless. Preliminary research remains classified under agreements between major space agencies to prevent destabilizing competition. Incredible properties that make vacuum metastability fields the ultimate space treasure include their ability to provide unlimited clean energy without fuel, waste products, or environmental impact. Unlike every other energy source, vacuum fields don't get depleted when energy gets extracted because they tap into the fundamental energy content of space-time itself. The extraction process doesn't require rare materials, complex fuel cycles, or massive infrastructure installations. Computer models suggest that vacuum energy extractors could be built using common materials and operate continuously for millions of years without maintenance. Specific details about this discovery reveal that vacuum metastability fields form naturally around certain types of neutron stars where magnetic fields reach strengths that alter the quantum properties of empty space. These magnetic fields create regions where virtual particles that normally appear and disappear in microseconds become stable enough to extract energy from their interactions. The process involves quantum field fluctuations that operate below the level of atoms and molecules, accessing energy that exists in the structure of space-time rather than in material substances. Research efforts have intensified dramatically since the initial discovery because scientists realized that artificial vacuum metastability fields could be created using technology that might be achievable within decades rather than centuries. The key involves generating magnetic field configurations that mirror those found around magnetars using superconducting electromagnets arranged in specific geometric patterns. Laboratory experiments have successfully created microscopic vacuum fields that demonstrate energy extraction on scales measurable with current instruments, proving that the effect can be replicated under controlled conditions. Immediate research programs operate under classification levels that restrict information sharing even between allied nations because vacuum energy technology can eliminate resource scarcity completely. Countries with access to unlimited clean energy could desalinate ocean water to end droughts, power massive industrial operations without environmental impact, and provide energy-intensive space propulsion systems that make interstellar travel economically feasible. The geopolitical implications are so significant that research funding comes directly from national security budgets rather than civilian science programs. Multiple global challenges can be solved simultaneously through vacuum energy applications that address climate change, poverty, and technological limitations using a single breakthrough technology. Unlimited clean energy eliminates carbon emissions from power generation while providing enough energy to remove carbon dioxide from the atmosphere using direct air capture systems. Desalination powered by vacuum energy could provide fresh water to every region on Earth regardless of local climate conditions. Space exploration becomes economically viable when spacecraft can carry vacuum energy extractors that provide continuous power without fuel limitations. Agricultural applications of vacuum energy could transform food production by powering indoor farming systems that operate independently of climate and weather conditions. Vertical farms powered by vacuum extractors could produce crops in Arctic regions, deserts, or urban areas without depending on fossil fuel transportation networks. The technology can eliminate energy costs from food production while providing controlled growing environments that maximize crop yields regardless of external environmental conditions. Manufacturing processes would undergo complete transformation because unlimited energy removes cost constraints from energy-intensive production methods. Materials that currently require enormous energy inputs to produce become economically viable when energy costs approach zero. Advanced materials manufacturing, metal refining, and chemical processing become profitable regardless of energy requirements, opening possibilities for producing materials and products that remain too expensive using current energy sources. Space colonization becomes practically achievable when vacuum energy extractors provide unlimited power for life support systems, manufacturing facilities, and transportation networks throughout the solar system. Colonies on Mars, the Moon, or asteroid mining stations could operate independently without requiring fuel shipments from Earth. Spacecraft powered by vacuum energy could maintain continuous acceleration for months, reducing travel times to other planets from years to weeks while carrying enough power to operate advanced life support and communication systems. The discovery reveals that empty space itself contains more extractable energy than all the antimatter, rare elements, and exotic materials in the universe combined. This represents a fundamental shift in understanding cosmic value. Because the most precious resource doesn't exist in rare objects scattered across space, but in the fabric of reality itself, accessible anywhere humans develop the technology to extract it. These discoveries represent a fundamental shift in how we understand cosmic wealth and human potential. The universe contains materials and energy sources that dwarf every earthly resource, from antimatter worth trillions per gram to vacuum fields that could power civilization indefinitely. Space holds solutions to problems we thought were unsolvable. Unlimited clean energy, revolutionary materials, and technologies that could transform how humans live and explore. The next few decades will determine whether humanity can access these cosmic treasures or remain limited to admiring them through telescopes. Every space mission and astronomical observation brings us closer to breakthroughs that could reshape civilization completely. The race has already begun between nations recognizing that cosmic resources could determine global leadership for centuries. These discoveries prove the universe offers wealth beyond imagination for those bold enough to reach for it.